Okay. Just trying to mute every other person. Some kind of background noise. Okay, so today we're going to be looking at energy efficiency, basically for industrial applications. Okay, when I say industrial application, that does not mean that it does not also include the things that we do in the house or in our families, in the homes. Okay, some of them cut across, but basically we're going to be looking at energy efficiency as it applies to industries and all of that. Okay, so the objective is to gain quality understanding of industrial processes. If you have to, now the reason why it is very, very important for industries, but that's where the bulk of energy consumption is taking place. Okay, if you come to a family house, a residential apartment, I mean, the energy consumptions are minimal, you know. But when you go to industry, that's where you see a huge consumption of energy. And if you're able to save 2%, I mean, just 2% of their energy consumption, that would translate into a huge amount of money. And that's why it's very, very important that we pay attention to this. We try to understand how these industrial processes, how they operate. The motors, the fans, the drivers, I mean, all of those processes. We need to understand how they operate, how they consume energy, okay? So that's why it's very, very important for us to understand this. Now, it's also to learn industrial energy efficient practices and conservation measures. Now, to prepare participants for professional certification exam, such as the Certified Energy Manager or the Certified Energy Auditor, okay? So this training will also enable you to gain knowledge that will enable you, go in and comfortably write your certification exam, without having to write it 2 times. Okay. So it is also to equip participants who wish to conduct energy audits in industrial facilities with a sound knowledge of industrial energy processes. So let us just talk a little more of what energy efficiency is. I know many of us already understand this concept, but let me just, run through it. I may not explain in full details. I mean, there are literature here they can read to understand. Okay. So the goal of energy efficiency program is to maximize productivity of energy by keeping waste as low as possible, thereby increasing business profitability and then providing solutions to environmental challenges such as global warming. We all know this. Now, it is an ongoing program that is actually never finished. Energy management in an industry is something that is, continuously running. It's never finished. Okay. So if you are going to be contributing meaningfully to a successful energy management system in your business, workplace, or elsewhere, obviously you must first understand the basic concept of energy and energy efficiency. Yes, they will try to talk about energy in itself, not just focusing on energy efficiency, but energy as a general principle. So what is energy efficiency? Energy efficiency refers to the efficient conversion and use. Now, the emphasis is on efficient conversion and use of energy, and it's a measure of the productivity provided per unit of energy consumed. This definition is important for you to be able to understand or appreciate energy efficiency. It employs devices and practices that result in less energy being used and energy being used for the same task and function. I don't want to just read through all because it's something anyone can read and understand, because there are more important parts that I need to explain very well in terms of the formulas that we're going to use and the calculations. So just permit me to skip all these literatures. You can read them on your own and understand them, please. So this is energy efficiency labels and ratings. Some of us are already familiar with this. So countries around the world, who are serious in climate change and energy efficiency, they have introduced a label, to help their citizens identify energy efficient appliances. So when you go out in the market to buy your fridge, your TV, okay, so they have mandated the manufacturers of these appliances to put their energy consumption characteristics such a way that it is easier for the buyer to understand, and you can easily compare which one is more efficient and not, right? So fortunately, in Nigeria, we have also started applying that rule. We've started, if you look here, you're going to see building energy label. This is Nigeria. So, but this is applicable for air conditioning systems and fridge. I think so. It is not yet dominance. I mean, meaning that you cannot see them in the market already, but it's something that is a work in progress. Okay. America, they have Energy Star, to help them understand the energy efficiency status of whatever you're buying. This is for India. I think this is also applicable for America. So let me just go ahead. So energy efficiency potential in Nigeria power industry. So I think I explained something like this yesterday about power generation. So when you're generating electricity, you start off with 100% energy in the form of gas. In the case of Nigeria, most of our electricity, 70% of our electricity, on-grid electricity, comes from gas. Okay, so that gas has to be burnt. Okay, it has to be converted into thermal energy, and then the thermal energy has to be converted into mechanical energy. Okay, now you begin to appreciate the level of losses that is going on before this electricity now gets to you in your home or in the office. So from mechanical energy, it's now being converted into electrical energy, and by the time all these processes has been completed, you have only 32% of the original energy that you started with. Okay, so you have to go through transmission and distribution losses, and then by the time it is getting to you at the end point, you have about 17% of the electricity. Now you started there with 100% energy here. Now you're ending up with 17% energy in the form of electricity, right? So what if you could cut off all of this process, all of these conversion processes? If there's a way we could just convert gas straight to electricity without passing through any of those thermal, mechanical, and all of those things, that would be the ultimate. But unfortunately, there's no such technology yet. Okay. So, but what this helps us to understand is like, for every unit of electricity that you save on the demand side, for every unit of electricity that you save on the demand side, you're actually saving 4.9 of the electricity that is wasted to produce that one that you actually consume. I don't know if that makes sense. If you save 1 unit of electricity on your in your house or in your office, that is on your demand side. You're not actually saving 1 unit of electricity. You're also saving 4.9 units that was wasted to generate that one. So you can see the impact of saving 1 unit down the value chain in terms of the gas that was burnt, in terms of the infrastructure that was built, and all of that. Okay, so this is how significant it is. And the best way to save energy is, I mean, at the demand side, not necessarily at the demand side. If you can save it at the supply side, I mean, before it even gets to you, that's best. Okay, and that's why it's important that we are careful how we use energy in our homes. Okay, because a lot of energy are being wasted to even deliver that 1 unit to our offices or homes for our consumption. Let me not speak so this is another way of presenting what I've just explained above. So energy efficiency potential in Nigeria. The potential of energy efficiency in Nigerian industry is huge. According to UNIDO, between 25 to 40% in developing countries, and Nigeria, of course, is a developing country. So it is also applied that 25 to 30 to 40% of savings is achievable in the Nigerian industries. Installed machinery is often outdated. Processes might run effectively, but often not efficiently. There are two different things. Running effectively and efficiently are two different things. Thus, over 40% of total energy use is wasted in old, obsolete, and inefficient equipment. Let me just skip all of this story. Now, these are the kind of policy that we already have in Nigeria that supports energy efficiency and renewable energy. Okay. Unfortunately, none of them has been gazetted, in the sense that none of them has been transformed into a law that is mandatory. So it is a policy, it is not enforceable. It's just a policy document. So we have the National Renewable Energy and Energy Efficiency Policy. Again, like I said, it is a policy, so it is not enforceable. Okay, so we now have again the National Energy Efficiency Action Plan. Now, this is an action plan, it's not a law. We have the National Determined Contribution. Now, this is part of our commitment to the Paris Agreement in 2015. Okay, then we now have the National Industrial Policy. All of these are existing policies that support energy efficiency in Nigeria. This is an overview of the NRE. take all of it. So now the next question is, what actually causes this inefficiency? What introduces inefficiency in the systems that we operate, okay? So inefficiency of energy are induced by two primary factors. One of them is technical losses and the other one is inefficient behavior, okay? So I try to put that in a simple equation. So energy in, so if you're looking at your facility, your entire company as a facility, the energy that is coming in into that facility should equal to the energy that is going out. Somebody might begin to wonder, but how does the energy go out? I don't see them going out. Yes. The energy that comes in, they also go out. They don't stay within your facility. All right. So how do they go out? Mostly in the form of heat. Okay. The energy that goes into your laptop leaves your laptop in the form of heat. The energy that goes into your television leaves your television in the form of heat and sound and other maybe mechanic, if there are moving parts inside your television, you know, I mean, whatever it is, they also live in those forms, right? So if we expand that formula a little bit, the energy that comes into your facility is equal to the energy that you use usefully, okay, plus energy that you use but you wasted it. So if you leave a light bulb on in a room that is empty, okay, it's being wasted. You use it, but it's wasted, right? So it also has to be included in this equation. Plus losses. Now losses, I try to define what losses are here, okay? So the losses here are technical losses, okay? So they are the energy used to overcome resistant forces, such as frictional forces or resistant forces or whatever kind of forces. Now, these are technical losses that cannot be avoided totally. You can reduce them significantly, but you cannot avoid them totally. But this other one, energy use that is wasted, is as a result of inefficient behavior. This is a human factor, okay? And it's very, very important that we pay attention to this, okay? Before we give more attention to the technical losses, we give more attention because this one usually presents low cost measures or even no cost measures for you to save this energy, okay? So it's very, very important that we pay attention to that. Okay, I think I discussed about the coefficient of energy efficiency yesterday, where I talked about that it is the useful energy that you use divided by the energy input. I made mention of this yesterday. If you want to determine the efficiency of any system, okay, in terms of energy, it is usually the useful energy or the useful work that you do with energy divided by the total energy that you actually put to give you the efficiency of that system. Okay, first of all, the system boundary have to be determined. So let us go into the main view, which is energy efficiency in the industry. Okay, so let us start from the first, from combustion, fuels and combustion. Let us start from there. Okay, so combustion is simply a chemical process of converting hydrocarbon fuels to thermal/heat energy. Okay. Now, in industry, there are processes whereby you need to combust fuel to generate thermal energy, especially for boilers. That's where mostly the primary focus of combusting fuels in industrial processes to generate thermal energy in terms of steam, hot water, or whatever it is. Okay. So, like the statement right is a chemical process. Okay. So this is a little bit of chemistry here. So you see methane, CH4 here, plus oxygen, normal combustion equation. So when you combine these two of them, this is your hydrocarbon plus your oxygen, you know, then you now produce heat plus water vapor, and then of course the CO2. So this is just a normal combustion equation. So now let us look at combustion efficiency. Okay, so if you're combusting this fuel to generate thermal energy, what are the ways through which waste can occur in this system? Okay, so let us look at these different categories of flames. Okay, so number one, you're going to see, you see number one, you see number two, you see number three, and up to number four, right? So if you look at it, you can easily tell that number four is the most efficient combustion process. Okay, Why number one is the least, is the worst, is the most inefficient combustion process. So our desire is to maintain the number four combustion process. Okay. So number four, what actually makes it look the way it is now is because it has a complete combustion. So all the fuel that goes into that combustion processes, we are kind of depleted to release their energy content. Okay. Whereas number one, not all the fuel were burnt down to reduce the energy content. So some of the fuel just came in and they also left. So the energy content was not realized. That's what number one really means. And if you look at the description I have here, complete combustion, you have the blue flame, which is the number four. You have no residue. Okay, so the fuel is completely burnt. You have a higher temperature because the fuel releases all of its energy. Then it has a high efficiency, right? Whereas for number one and number two, and maybe to some extent, number three, not completely inefficient though. So you have the yellow/orange flame telling you that it's an incomplete combustion. They have black residue or smoke, right? They have a lower temperature, but the fact that all the energies are not released. The energies are actually wasted in this case because the fuel came in and it left with some of the energy content, and it also produces toxic gases, which is carbon monoxide. So how you know when a combustion is incomplete is also when you find the presence of carbon monoxide. You know that it's an incomplete process. Okay. So combustion efficiency. What is complete combustion? To ensure complete combustion of a fuel, of the fuel used, combustion chamber are supplied with excess air. Excess air increases the amount of oxygen to the combustion and the combustion of fuel. Okay. When fuel and oxygen from the air are in perfect balance, the combustion is said to be stoichiometric. Don't mind the big grammar. What it's actually saying that when the combustion, when oxygen and the air, when they're in perfect balance, when they're in perfect harmony, that's the right quantity, you're actually going to have a complete combustion. So when you have a complete combustion, it is known as the stoichiometric process. So the combustion efficiency increases with increased excess air. Now, because you don't know the exact amount of air that you can add to equate the number of to deliver the right quantity of oxygen. Remember that oxygen is also, you're adding air because of the oxygen that is in the air, right? And air has about 21% of oxygen, about 71% nitrogen and all of that. So, but you don't know the right amount of air that you want to add that will enable that fuel to burn completely. So it is advisable that you add excess air. So instead of achieving under combustion, it's better you have more of excess air. Okay, but too much of the excess air is also bad. So there are ways to measure some of these things. Anyway, I will come to that. But I'm just trying to introduce you to the concept of excess air, why you need to add excess air to your combustion process, just to make sure you achieve a complete combustion. So until the heat loss in the excess air is larger than the heat provided by the more efficient combustion. So I will explain this. I think I've actually explained it for the fact that you don't know the amount of oxygen that you need to achieve complete combustion. It necessitates the fact that you have to now include excess air. So excess air is needed to achieve the highest possible efficiency for some common fuel. So let us look at for some of the common fuel. So for natural gas, it is advisable that you add about 5 to 10% excess air to achieve complete combustion. Then for fuel oil, it is advisable that you add about between 5 to 20% excess air. Then for coal, it is advisable that you add about 15 to 60% excess air to achieve complete combustion, right? Now, if you look at this diagram here, if you look at this horizontal axis, this is excess air, and then if you take it to the left, you're going to see excess fuel, right? So at the point where you have complete combustion, where you have the highest efficiency, is at this point. Okay, you see the red line, which is the efficiency. Okay, this is just a plot trying to correlate the impact of oxygen, fuel, and then of the impact of oxygen and fuel to the efficiency level of your combustion. Okay, so this is efficiency level. The green line is the fuel. Okay, while the blue line is the oxygen. Okay, so if you look at the point where you have the highest efficiency, which is at this point, you find out that the oxygen and the fuel are almost, I mean, they're in close proximity. Okay, they're not exactly the same, but because we don't know when they are going to be exactly the same thing, but they have to be as close as possible. Okay, but if you keep on increasing your oxygen, that is, if you keep on increasing your air, you see this oxygen. If you keep on increasing your air to increase the oxygen, you see your efficiency will begin to be drop at this point. Okay, so that's just what this graph is trying to illustrate. So how do we measure combustion efficiency? Okay, there's a tool that enables us to measure that. Okay, and okay, so for you to be able to measure your combustion efficiency, you need to insert an electronic probe into stack to measure. Now, what is stack? The stack is the exhaust pipe. If you're combusting a fuel in a chamber, there is an exhaust pipe. So for your generator, your generator is an internal combustion engine, then it has an exhaust pipe. Okay. So if you want to measure the efficiency of that combustion, you insert this probe into your exhaust pipe. Okay. So the exhaust pipe, the probe will not analyze that exhaust gas. It will check if there is carbon monoxide. So if there's carbon monoxide, it means that the combustion is not complete. Okay. It will check the NOx or the SOx, right? Now, the presence of these gases is an indicator that there is an unburned fuel in your stack gas. That's what it means. Okay. So the stack temperature rises above combustion air inlet temperature. So now what this is saying, if you now check your stack temperature, okay, if the temperature is high, if the temperature of the temperature of your exhaust gas, okay, if it is higher, sorry. Okay. So I'm trying to this particular statement of stack temperature rise above combustion air inlet temperature. Now, when you increase the temperature of your excess air or the oxygen that you're putting into your combustion chamber, right? If you increase the temperature, you can actually increase the efficiency of that combustion process. I will explain this further when we get to the point where we're going to be talking about boiler itself. Now we're talking about the combustion chamber here. When we get to the point where we're talking about the boiler itself, I will explain this further. Okay. But for now, just understand that for you to know if your combustion process is efficient or not, you need to insert a probe. So you're looking out for some element like the carbon monoxide level, the NOx and the SOx level. Now, all these are elements that help us to indicate if the combustion was actually complete or not. So now we're going to talk about boilers. Combustion that we talked about earlier is just a subcomponent of a boiler. Okay. So we're not going to look at it in totality, the boiler as a whole. Okay, so we're still going to touch a little bit on that combustion sector. So boilers are needed to generate steam. Now, steams are heat carrier for industrial processes. The same way your wires will carry electricity to your industrial plant. That's the same way your steam will carry heat from the boiler to your industrial processes, where you need to add heat, where you need to do drying. Okay, so that's what heat does. Okay, and that's why you need steam in an industrial process. Okay. So for boilers, you have heat carriers. Now, heat carriers are the thing that actually carries that heat from the boiler, from the boiler to the point, where you need to utilize that heat. Maybe you want to do a drying process. You want to dry maybe a certain industrial raw material, okay, and you need heat to go through that raw material to extract the moisture content, okay. So now these are the things that can carry those heat for you. So you have water, hot water, you have steam, you can have thermal oil, you can also use air or other fluid as a heat carrier. Now, these are the kind of fuels that you use for your combustion processes. You can use solid fuel, which is coal, biomass, municipal waste. You can use liquid fuel, which is liquid oil, liquefied petroleum gas, or LPG. Now, all these are kinds of fuels that you can use for your combustion chamber or your burner. So heating surface layout. Okay, so there are two types of heating surface layout, which is shell type and then water tube boiler. Okay, I will show you a picture of these two kind of heating surface layout in the next slide. Okay, then of course you have pressure. You have low pressure boiler. They have high pressure boiler. Okay, so I talked about the two type of boilers. I say I'm going to explain that here. Okay, so there are two basic type of boilers. Okay, so you have the fire tube boilers and then you have the water tube boiler. Okay, fire tube boiler and then water tube boiler. Now this is a clear explanation of what they are. Okay, so now this is water tube boiler. If you notice, you find out that water is actually passing through the tube. Why? Now this is your funnel. This is where you're heating. This is your burner. This is your burner, right? Heat is being generated here, right? But you need to transfer the heat into a carrier. So in this case, it's water. Water is our carrier here. So water passes through the tube and absorbs the heat. Okay, and then before this, you see the furnace is here, right? Before the hot gas that is coming out from this furnace, before it passes through this tube, it will now lose some of the heat to this water. Okay, and then it will now go out here. Now this is a stack. This is a stack gas. This is hot gases that goes out. Okay, now this is a lot of waste. This heat that is going out here is a lot of waste. So part of our energy efficiency measures will be how do we recover the heat that is going out from here, right? Mind you that the water that is coming in through these tubes will have collected some of this heat to turn into steam or hot water, whichever one you desire. Okay, so now the difference between the water tube boiler and the fire tube boiler is just the opposite. Now in this case, notice that water is now in the shell. Okay, while the hot gases that is coming out from the fire is now passing through the tube. Okay, whereas in this one, opposite is the case. But here, water is like in a tank, then you're now passing hot pipes through the water to extract the heat, and eventually you have the stack gas that is going out from this vent here. Okay, so here, once this hot gas passes through this tube, they deposit their heat into this water, and the water boils and turns to steam, and then the steam goes out from here. Okay, so these are the two kinds of boilers that we have that are very predominant in the market. So you have the water type, and how do we describe it? Now, hot gases flow around tubes that are filled with water. Now, the tubes will be connected to a steam drum. Now, this is a tube that is now connected to a steam drum that is now going to pick up the steam and then distribute it to the industrial processes. Whereas the opposite is the case here. I think I've explained that here. But if at any point, if anyone has a question or you're not very clear about the explanation, please call my attention so I can provide more details. So just to make us understand what is happening in a boiler, okay, I have explained this yesterday. Okay, you have a water that you heat. Now, assuming that you have, okay, at this point, when you have 70 degrees, this 70 degree Fahrenheit anyway, but at this place, assuming that you have a water, just water normal room temperature, right? And then you start applying heat to it. The heat that you're applying to that water at that time is sensible heat, okay? That water will continue to heat until it gets to 100. When it gets to 100 degrees centigrade, you keep applying the heat, it's not going to increase in temperature anymore. But what's going to happen at this time is that it's going to use those higher heat that you're applying, change its phase. It will now change into gas, which is what we now know as steam. Okay. So from this point to this point, okay, you're still applying heat. Okay, but the heat you're applying at this point now is known as latent heat, not as sensible heat any longer, because at this point, change of phase is happening. Okay, so from here now, it's now fully gas, which is the steam that we want. So this is what is actually happening in a boiler. Okay, so we apply heat to change water from liquid phase to gaseous phase. That's exactly what is going on in a boiler. So let us look at heat flow equations. Okay, this is important because you'll be seeing a lot of calculations around this. Okay, heat flow equations. So Q is heat flow. Okay, it is equal to M. M is mass flow rate. Okay, mass flow rate. This mass flow rate can be for liquid, it can be for water, it can be for kerosene, it can be for diesel, it can be for anything at all. Okay, then you now have the CP. Okay, CP here means specific heat of the substance, whether water or whatever it is that you're using as your medium of heat transfer, right? So this is specific heat of it. Then temperature difference, that is the T. Okay, so if you're doing heat transfer, what temperature did you start with and what temperature did you finally end up with? Okay, so we need all of those parameters to be able to calculate our heat transfer or our heat equation. Now, this is for sensible heat only. You apply this equation for sensible heat. Okay, if it's for sensible and latent heat, okay, in this case now you're going to apply what we know as the enthalpy, change in enthalpy. Now, this change in enthalpy means the energy content of that substance at a particular temperature. Okay, so that's what this DH means, this change in enthalpy. The mass flow rate remains the same thing, but instead of the specific capacity and the T, that is change in temperature, you're now replacing this two things with change in enthalpy. Okay, so if you're calculating heat flow through surfaces, okay, so you're calculating heat flow not through water this time around, but maybe through a wall or through a wood or whatever it is. Okay, there's a different formula for that. In this case, you're going to now use quantity of heat, which is Q, is equal to U. U here is the coefficient of heat transfer. Every material has their own coefficient of heat transfer. So if you're given a question, you most probably be given the coefficient of heat transfer for the material that you're working with. Okay, then A is just is total surface area, of the material, and then the T is change in temperature. From what temperature to what temperature are you transferring the heat? Okay. Now this is for heat flow through surfaces. So just keep in mind of these formulas. You may not necessarily need to cram them because in any of these cases, you always have materials to refer back to. So let us do a simple test question here. So heat which when added or subtracted does not result in change of temperature is called what? Please, I need someone to respond to this. Let me know I'm not talking to myself. Please, if you want to respond, unmute the mic and respond, please.
It's latent heat.
Okay, thank you very much. So it is latent heat, okay? Yes, thank you very much. I heard you. Thank you so much. So it's latent heat, okay? So let's just proceed. If anybody is confused about this, please don't die in silence. Just speak up so we can explain it, because my assumption is that we understand it now. The whole essence of this question is for us to understand the two types of heat. There is sensible heat, there is latent heat. So if you understand these two types of heat, it's going to help us in our calculation. So here's a sample question. How much heat is required to raise the temperature of the water flowing at 100 kilograms per hour from 20 degrees centigrade to 100 degrees centigrade? Now, I want to say something here, that these sample questions and the examples that we are seeing here are not just by our own formulation. These are actually real examples. These are actually real questions that was pulled out from CE exam and CEM exam. Okay, so These are typical exam questions that you're going to see. Okay, and even when you go to industry to an audit, these are typical calculations that you would normally have to carry out. Okay, so that we are presenting this, it does not mean that we just like to calculate. You know, some people say that engineers we do like calculations and stuff like. No, it's not because we so much like to calculate. If you go to industrial process, you're going to do this calculation. So that's why it is important that we understand this calculation, this formula. Okay. So we are giving a head up here. We are giving the specific heat of the water, which is, it doesn't change. The specific heat of water is always 1.2 kilojoule per kilogram per degree centigrade. Okay, so let us look at how we solve this question. Okay. So first thing that we're going to notice that it is a sensible heat. You're moving from 20 degrees, right? And it's water. Water at 20 degrees centigrade is still liquid. Up to the point you have 100 degrees centigrade, it is still liquid. Then from 100 degrees centigrade, it begins to turn to gas. So we know it is a sensible heat. So we go and pull out our equation for sensible heat, which is the first equation there, which is M times Cp times dt, right? So as simple as it is, we put that equation and then we impute our values, the values that we know. We know the mass flow rate, which is 100 kilogram per hour, right? We know what the specific capacity is we have been given, okay? And then we know what the, we know what the temperature difference is, yes. This 80 is 100 minus 20, right? Maybe I should have written it 100 minus 20 so that it doesn't consider anyone. We know what this temperature difference is. 100 minus 20, that is 80 degrees centigrade. So when you press your calculator on this, you're going to get 33,600 kilojoule per hour. That is quantity, that is the heat. Okay? That is the heat that is transferred. Okay? Or rather, the amount of heat that is required to raise that temperature of water from 20 to 100 degrees centigrade. So this is the quantity of heat that is required to do that job. So, but again, you will find out that in this our equation, it is in kilowatt. It's fine and good. This answer is correct, right? But if we want to convert this now to normal conventional electrical unit, which is the kilowatt, okay, then we can do that conversion. If you look at conversion table, you will know that 3,600 kilojoule is equal to 1 kilowatt hour. Okay, so if we now check for 33,600 kilojoule, if you convert it to kilowatt hour, you're going to have 39.33 kilowatt hour, right? But you know that we still have per hour here, okay? So you have to divide it again by the hour, okay? Which is what we did here, 3.33 kilowatt hour per hour. So the hour will cancel the hour. You're left with 3.99 kilowatt, right? So that is the quantity of heat in terms of kilowatt that is required to raise this water from 20 degrees centigrade to 100 degrees centigrade. Any questions so far? I guess no. Okay, thank you. So let us look at energy losses in boilers. Now we've talked about boilers and the principles, how boilers operate. Okay. Now let us look at how energy losses occur in boilers. So back to our two types of boiler. Okay. So here on this column, you're going to see the sources of energy loss. In this range, you're going to see the estimated percentage of losses that are occurring as a result of these sources. And here you're seeing factors, okay? I will explain this. So for the first one, you have heat in fluid gases. Heat in fluid gas. Now, what is the fluid gas? I talked earlier about these gases that is exiting from this point. After you've done the heating, some of the heat has been transferred to form the steam. Then the gas from the combustion will now escape. So when the gas from the combustion is leaving, it still contains a good sum of heat. So how do you capture that heat? Okay. So you can actually save up to between 8 to 35% if you can capture the heat. from that exit gas. Okay, so the factor here is exit temperature. So the exit temperature is high. Okay, now you are going to see another thing, excess air. When you add too much excess air, right? What that means is that you're also going to have higher heat that is going out from here. And that's what I was trying to explain the other time when I was talking about when you want to measure when you insert your probe to measure the characteristics of the gas that is going out from your egg from your stack here, right? So if you put that probe and you find out that the temperature is so high that you're seeing a high temperature of gas that is going out, what that tells you that maybe you're adding too much of excess air. So too much of excess air will just push more of the heat that should have been been absorbed by the water. It will just push more of that heat into the stack, and it will all escape, into the environment. So if you look at your stack temperature and you're seeing a very high temperature, it tells you that look, there's a lot of wastage that is going on at this point. Okay, so there is heat with moisture content of fluid. Okay, this is also part of the stack exhaust. I mean the gas that is going out from the exhaust. So it's still part of it. So let us look at incomplete combustion. We have an incomplete combustion. What does this tell you? So you can, if you have an incomplete combustion, you can actually recover up to 1% energy savings. Okay. And how do you know when you have an incomplete combustion? When there is carbon monoxide in your fluid gas, it tells you there's an incomplete combustion. Carbon monoxide tells you there's an incomplete combustion. But if you're seeing carbon dioxide, then that means a complete combustion. So there's what we call boiler blowdown water. Okay. Now, blowdown water, what this simply means is that when you have a boiler, now what's happening in your boiler is that you're transforming water into steam, right? Now, sometimes you have scales. Okay, if you have been dealing with water, even in your kettle, depending on the kind of water you have, if you keep boiling water and the water keeps evaporating, turning into steam, sometimes you find out that you have scales, residues, right? Now, sometimes if you don't remove those kind of residues from your boiler, it will cause damage. So those residues, you need to remove them, and that's why we have the need for blowdown. We usually call it total dissolved solid blowdown. Okay, total dissolved solid (TDS). Okay, so we need to remove them, and that's the essence of blowdown water. So when you're blowing down those total dissolved solid, it also contains some amount of heat in that water that you're blowing down. You need to recover them. Okay, so what are the factors? Correct checking and maintenance. You need to do correct. I mean, if you're doing your blowdown, you need to do a correct checking to make sure that you're not losing so much amount of heat in your blowdown procedures. Then you have radiation from boiler surfaces. Of course, this is your boiler. The surfaces, you can have radiations on the surfaces. So what do you do in this kind of case? You need to insulate. You need to case your surface. Okay, and in that case, you can actually recover up to 1 to 3% of heat. Now, combustibles in ash. Now, this is where I talk about incomplete combustion. Okay, so when you've done your combustion here, you've burnt your fuel. Sometimes you find out you still have some combustibles inside the fuel, which means you have not actually finished the whole complete combustion. Okay, so it's another way of loss. Okay, so what are the factors here? Poor air distribution, which means there was not enough air for that fuel to achieve complete combustion. That's what it means. So another source of heat loss is part load operation. Of course, we know that when you're operating any appliances or any equipment at part load, you know it is not at best efficiency. It's not the best efficiency practice. Okay, so the same thing is applicable to the boiler. When you're operating a boiler at a part load, okay, you're not operating at the best efficiency method, okay, or best efficiency level. So energy saving opportunities. Let us look at how we can actually save some of this energy, because I've talked about how some of these losses occur in boilers. Let us talk about how we can actually save energy in this boiler. The first of them is the installation of economizer. I will show you a diagram of what economizer is in the next slide. Okay. So we need to install economizer. Okay. Now, economizer is just something that we'll use to capture the heat in the exhaust gas. Okay, we capture the heat with water. So the exhaust gas, let me show you. Okay, so this is what the economizer is. So this is a boiler. Now this is the exhaust gas, right? So you pass water through this exhaust gas to recover the heat, okay, from this exhaust gas. So when you recover the heat, you now pass that water, okay, into the boiler itself. Okay, so before the water gets into the boiler, the water is already hot, right? So you don't need so much heat to raise it again to 100 degrees centigrade. That's how you save energy. Okay, you reduce the amount of heat that you need to heat that water to 100 degrees centigrade. So first of all, you preheat the water using the heat here that would have otherwise gone out. So that's what we mean by economizer. Okay, so let me come back to this place. So you can actually save between 3 to 8% by doing that. So combustion air preheat. Now, what this is saying that before when you're doing your combustion, it's a combination of oxygen, right? So if you also preheat the air that you're injecting into your boiler, it's also going to improve the efficiency of your boiler. Okay. So what that happens is that now this is also this is your stack, this is your exhaust pipe, right? So unlike the economizer I talked about, in this case you use air instead of using water. If you use water, it's an economizer. But if you use air, it is called a recuperator. Okay. So you pass air across the exhaust gas, exhaust pipe, okay, to absorb the heat, okay, that would have been lost to the environment. Okay. So when that air blows through that exhaust pipe, it becomes hot. So you now inject that air into your combustion chamber. Now this is your combustion chamber. You inject the air into your combustion chamber. Now, because that air is coming into your combustion chamber hot already, right? It's going to improve the combustion efficiency of your boiler. So that's what the combustion air preheat means. So you can also do combustion control, okay, in terms of your excess air, how much excess air you add into your combustion and all of that. You can do that. Then blow down optimization heat recovery. What this one means that I have described what blow down means, right? So when you're doing your blow down, make sure that you recover the heat that is going out from the water that you need to do your blow down. Okay, so you need to recover that heat. So installation or repair of installations. You know, the boiler systems is a heat system. So if you don't insulate the walls of your boiler, you're going to lose more heat to radiation. So it is important that you do installation of your boiler to make sure that you don't lose heat that would normally go into because the whole essence of having a boiler is to transform water into steam, right? So we want to make sure that as much heat as possible goes into that process and not any other thing. Okay, so we need to installate our boilers properly. You can do load management. Okay, you don't operate your boiler on part load. It's not hygienic. It's not efficient to do that. So the other one is to install VSD for fans and blowers and pumps. Now, when we are talking about boiler, there are other components of the boiler system apart from the burners and the pipes that transport the steam and all of that. There is also fan, there is also blowers. Okay, so for those fans and blowers, you might need to install variable speed drive or variable frequency drive. They all mean the same thing, to be able to control them so that it can match the load on the boiler. Okay. So this is a more capital intensive procedure where you need to do your boiler replacement. Okay. And then finally, general housekeeping measures. You know, we save you about up to 5% and all of that. I've explained what the economizer is, and I've explained what this recuperator is. Now, all these are ways of recovering waste heat in a boiler. Now, let us look at the steam system itself. Now, we've talked about boiler. Now, let us look at steam system itself. Now, if you look at this diagram, you'll find out that it is a system, and within this system, you still have the boiler. Okay, so boiler is what actually generates the steam. So we want to talk about steam now, not about the boiler. So when boiler generates this steam, it turns water into steam. Now, this steam has to be transported from the boiler unit to all areas of the factory where it is needed for different heat applications. Okay. Now, there is a problem here. When this steam flows through this pipe, into this industrial application, sometimes they condense, they change back into water, right? While they are in the process, they change back to water. Now, if you don't remove that water, it will create a problem for the industrial process. So it becomes very important that when this steam, when they condense and return back to water, you have a way of removing them from the process. Okay, and that is where steam trap comes to play. Okay, I'm introducing another concept, steam trap. Steam traps are used to remove condensate in the steam system. Okay, so now this is a steam, it flows through this red line, it comes down here, this end use where you have heat exchanger, right? Now, after this heat has been used, okay, it loses part of its heat. It now condenses back to water. So you now see here, we have steam trap. Steam trap enables the water to escape from the system. So this is another process. So you have several steam traps across the processes. At every point, you know that the steam is going to condense and form water. You put a steam trap to remove the water. Otherwise, it's going to cause a problem. That's what we call water hammering. Okay, it will be making noise in the pipe as it's transport, as the steam flows along the pipe. It's going to be making undue noise, and it can also create damage. And it's also a poor quality heat. Heat in the form of hot water is a poor quality heat compared to heat in the form of steam. So we want to get rid of that poor quality heat, which is now in the form of water. So that is why it is important to remove water that has returned back to, steam that has returned back to water. And we call them condensates. Okay. So if you see here, you're going to see what we call condensate receiver tank. Okay. But here, when you recover this condensate, you're not going to throw away this water because it's a very pure water. It's pure, right? It does not have impurities. So what you do, you have to return it back. You have to return it back to the steam. You have to return it back to the boiler to turn it back again into steam. So it's a continuous process. It's a circular process, right? So look at the condensate water now. If you see now, this is a recovery. You have to send it back into the boiler. But before we send it into the boiler, you will not see that it passes through an economizer. I remember I explained what economizer is. That water passes through the exhaust pipe of the burner so that it can also acquire some of the heat in the exhaust before it goes into the boiler. So you don't need so much heat to raise that water to 100 degrees centigrade. Right? So this is how you save energy in a boiler and steam system. One is that you don't throw away the condensate. You don't get rid of the condensate. Two is that you have to recover the exhaust heat from the exhaust pipe through either economizer or through recuperator. These three things should stand out. Then, of course, you must do your installations. You must insulate your processes. Okay, so this is about steam and boiler and steam distribution. Okay, so let us look at the pros and cons of steam system, right? So it has a high heat content, small pipe. You begin to wonder why does industry, why do they use steams and all of that and stuff like that? It's almost unavoidable. They use steam for industrial process. Like if they need to do drying, if they need to do so many, they need to add heat to some certain chemical materials, to achieve certain reactions and stuff like that. They use heat. They use steam to transport those heats to those processes. Okay. So the reason why a lot of them use this steam boiler is that it has a high heat content, okay, and high transfer rate, because steam has a very high amount of heat content. It can easily transfer that heat into another body, okay, and that's why they prefer to use steam for this processing. And then it is sterile, meaning that it's free from every bacteria and stuff like that. And the steam is flexible. Then what are the cons of steam? It's a very capital intensive system. Okay, it operates at a high pressure, which is a danger. Okay, and the water treatment is required. If you're introducing water into your steam system, you need to treat that water. Otherwise, when the water evaporates, it will leave some residues that are undesirable in your steam system, which will definitely cause problem. even though you must have treated your water before introducing them into the steam system, sometimes they still have that residue, which is the reason why you need to do blow down, like I explained before. You need to do blow down to eliminate those residues. Okay. So when you have high temperature of steams, what high temperature means is it's also equate to high losses. Okay. We have high temperature moving through a pipe. It also amounts to high losses because of the high temperature differentials. Unless unless you insulate the entire process very well, such that there is no, that interface with the atmosphere is minimal. So the losses in steam system can be as high as 40%. Okay, so the useful steam is about 60%. Then about 40% of it are losses. So how does this 40% losses occur? Okay, so let us look at how the 40% add up together. So condensate and flash steam account for 20%. I've explained to you what condensate is, right? Then flash steam, I think is in the next slide, I'm going to explain what the flash steam is and all of that. But essentially, there are leakages, right? Maybe you have holes in your piping system where through these steams can leak through and stuff like that. So when you have those kind of things, you have a flash steam, leaving the system from those kind of holes. Then you have steam generation. At the point where you're generating the steam, you have losses of between 13 to 15%. Then you have distribution and utilization. Some of the processes that you're using the heat to accomplish, some of them are inefficient systems. Like maybe your heat exchanger might not be operating properly. Maybe you have some kind of debris or some kind of thing covering the heat exchanging medium, so that it is not highly effective. So all of these are what causes this 40% losses. So this is condensate recovery. I think I've discussed about this already, and there is no point for me to repeat. But this is a more a wider view of what the condensate recovery is about. So it has been color coded. If you look at it, the blue ones are the condensate, which means they are the water, right? Then the red ones are the steam. Then the yellow ones are the vapor, somewhere in between, right? So you start from water. Now this is your boiler. This is your fire that is heating up the boiler. It transforms this water into steam, which is the red, and then it flows through the production processes and all of that. Then you have the steam trap. Steam trap that removes the condensate, which is now the water, and the water now returns back to the boiler. It's just a circular process. So condensate recovery. The condensate water contains up to 20% of the steam energy. That's the water that is now the steam that is now converted to water, and you're removing it through the steam trap. Still contains up to 20% steam energy. Returning this energy to the feed water tank preheats the feed water and thus lowers additional fuel energy input. I've explained all of this. The condensate water does not need to undergo further treatment again, because this does lower its treatment cost. I've also explained this. So this is just, I've explained a lot of, this is the TDS I talked about. The condensate water does not contain total dissolved solid. Thus, it reduces boiler's blowdown cycle. Okay. Remember, anytime you're introducing new water, fresh water into your boiler, the chances that you're also introducing total dissolved solid that can also impact your boiler, but your condensate that you're returning to the boiler does not contain TDS. So it's an added advantage, for the boiler. Then flash steam contains condensate that should be recycled as well. I've talked about flash steam, where you have holes maybe around your steam distribution lines, and you have this steam that are leaking and all of that. Then every 6 degrees centigrade increase in feed water temperature gives 1% savings in fuel. I cannot overstate this, right? Where I keep talking about recovering the heat from your exhaust pipe and then using it to preheat the water, your feed water that is going back to your boiler. Okay. Once you do that, you begin to save the amount of, you begin to reduce the amount of fuel you need to burn to raise the temperature of that water from 20 or 25 or 30 to 100. Now, let me talk about steam trap. I've told you what steam trap does. I mean, what it does, its function, essentially just to remove the condensate from the system, okay? Now, the problem is that steam traps can also create its own problem, okay? Now, steam traps are types of automatic valve that filters out condensate, that is condensed steam, and non-condensable gases, such as air, without letting steam escape, okay? So this steam trap, they remove this condensate without letting the steam escape. They just remove the water without letting the steam escape. So how does it do that? It has an opening. It just opens. So according to, let me read this. According to global study, steam leakage through orifice can be as high as 10% of consumption. So sometimes this steam trap can open to allow the condensate to go out. Sometimes it can fail to close. So when it fails to close, what happens? It remains open, and then steam that should go for production process will now begin to go out and begin to waste. Okay, mind you that this steam trap is an enclosed system. You're not seeing it. It's an enclosed system. Inside it, you have all the mechanisms that enables it to open, allow water to go out, and then it close back. But sometimes it might just open and then fail to close. The steam will just keep going out through that process. That is one. Two, sometimes it can also fail to open. Okay, so steam condensate will build up and it will fail to open to allow the condensate to escape. Okay, in which case the condensate will now remain inside your system, inside the steam, and it will now it will not affect the quality of your steam. Okay, and you will not get the desired production output that you need, right? So the steam traps needs to be taken care of so that they don't also introduce their own inefficiency into the system. So steam system improvement, use high quality steam traps. Like I said, you need to be very careful about the steam trap. Okay, so use high quality steam trap and establish a program of regular systematic inspection. This is very important because the steam trap, you're not seeing what is going on inside of the steam trap. So you need to continuously inspect it to make sure that they are functioning optimally. Okay, by inspection, testing, and then repair of steam traps. Then return condensate to feed water. I've talked about this. Now this is steam leak. Okay, this is steam leak. So when you see this kind of thing, just know that it's a waste of energy, right? So when I talked about flash steam, this is what it looks like. Okay, so when steam suddenly, when they suddenly expand, okay, they begin to condense very rapidly into water. Then you see them, it's like a mixture of steam and condensate, okay? Because ordinarily, you cannot see steam. Steam are invisible. But if you can see them, it is no longer steam, in which case it is now flash steam, which is what I try to explain here. So part of the energy efficiency measure is steam line installation, right? You need to insulate properly your steam line. If you look at these two diagrams, you see before and then you see after. Okay. So steam line installation continues. Now I don't know how many of you that are familiar with thermal image camera. Okay. Now this picture that you're seeing was taken by a thermal image camera. So you can find out that there's poor insulation here, right? And that's why you find out that there's a heat loss at this point. Okay. But again, if you now insulate properly, now look at the real picture here. You find out that there is no insulation here, and that's why you're seeing the heat loss here. So now in this case, now it's not being properly insulated to prevent this heat loss. So insulate properly. Okay. So let us look at heat exchangers. Okay. Now heat exchangers are used at various points in steam system to extract heat from the carrier. Remember that the boiler generates the heat. The boiler, it heats the water and then converts that water into steam. Then there's a steam distribution system that transports that steam from that boiler point to the point where it is needed for an industrial purpose. Now, at that point where it is needed for an industrial purpose, what you have at that point is heat exchanger. Okay. So heat exchanger extract the heat from that steam, okay, and transfer that heat into the industrial process that you want. Okay, and once that happens, part of the steam condense, they return back to water. And then you now have the steam trap to remove that water. Are you not seeing how everything is not tying up, from the boiler to the steam system, to the steam trap, now to the heat exchanger? They are all part of one process. They are all part of one industrial process. Okay. So heat exchanger is now what extract the heat from the steam and then convert that heat to your industrial processes. So for example, as maybe you want to dry, rice. Okay, maybe you finish parboiling rice and you want to dry the rice and you want to introduce heat, to dry that rice. So at that platform where you have the rice, you will now have what we call heat exchanger to extract heat from the steam and then convey that heat to the platform where you have the rice so that the rice can be dried with the heat, right? So that's what heat exchanger does. And in most cases, you have like maybe different type of heat exchanger. You have the shell and tube and so many type of heat exchanger. But this diagram here actually illustrates what heat exchanger is. So in this case now, you see steam that is coming in. So this is yogurt. Now, this is a yogurt processing company, right? So I think they want to heat this yogurt, yeah, right? Here's my question. So now steam is coming in here and it's going out as a condensate. So what you have here is a heat exchanger. So this heat exchanger will extract the heat and then pass it on to this yogurt. And by that time, the steam will now return back to condensate. Okay. So now the yogurt is coming in here cold, but it's coming out here as hot. Right? So what enables this to happen is the heat exchanger. Then the same thing happens in the cooling process. Okay. So in this case now, a cold water is coming in here. Okay, and is living in. So what is happening? You want to cool down this yogurt. At this point, you've heated the yogurt, but you want to cool it down. So you now apply cold water here, and the cold water is coming out here, not as cold water anymore, but as something that is now between cold and hot. Okay. So all of these things are the functions of heat exchanger. The same thing is happening in this case now, where you have a steam that is coming in, it passes through a heat exchanger, it loses part of its heat and it comes out as a condensate. So let me just proceed. If anyone has any question, please, or you need more clarification, please do it to stop me and then ask your question. So let us look at heat exchanger recovery. Okay. What places do you apply heat exchanger? Now let me make this statement. Remember when I talk about economizer, when you need to pass water through your exhaust pipe to recover the heat that is going out through your exhaust pipe, you actually, what you have actually done is to install heat exchanger around that point. Okay, so that water passes through the pipe and it extracts the heat from the exhaust pipe. Okay, so it takes the heat from the exhaust gas and transfer that heat to the water, right? And that's the function of heat exchanger. So that is exactly what is happening in this diagram that you're seeing here. Okay, I just thought I should also make that explanation. So this is a recuperator heat exchanger. When I talk about recuperator, I'm talking about using air to extract the heat from your exhaust gas. So you have your generator, but I'm just using an example that we can easily relate with. You have your diesel generator, you have the exhaust pipe. You now have something that passes air through that pipe, so that when the air is coming out from that pipe, the air is now hot, right? That is now what is happening in a boiler. We use air to extract the heat that is going out through the exhaust pipe, and we now inject that hot air into the combustion chamber, okay, to make the combustion efficient. So if you look at what's going on here now, this is exhaust gas that is going out, the red one, exhaust gas that is going out from the burner, from the boiler. Now this is air that is coming in. This blue color is the air, and it's cold. It's now come into this heat exchanger, and they make contact with the hot exhaust gas, and it comes out warm. Okay, so this hot exhaust gas now comes out cooler. I mean, it's no longer as hot as it is because part of the heat has been stripped off. So it comes out colder, right? And it goes into the environment. If we did not do this, the whole of this heat would have been lost to the environment, which is not good. Okay. So heat exchange recovery, common sources, compressor. Most of us use air conditioner in our house. I don't know if you have actually noticed how hot your compressors could be, whether the one on your fridge, your freezer, or your air conditioning system. Compressors are generally hot. So for industrial application, they are good places to recover heat. Okay. So another one is flue gas. Flue gas means gas that is leaving your exhaust pipe from your generator or from your burner. Okay. So that's a flue gas. Then the next one is waste water. If you have hot water that is being wasted, you can recover that heat from the waste water. Then you have oil cooler. If you look at your diesel generators, right? If you notice, you usually have to you need to add oil to your generators, and what that oil does is that it circulates around your generator and provides kind of lubrications around the moving parts of your generator. But what you also notice that oil usually gets hot, okay, and they lose those heats to the environment, right? So for industrial applications, if you have a large power plant, you can actually extract some of this heat from the oil, from the plants, and then use them either to preheat water, right? Or if there are places where you need low-grade heat, you can actually use them for those kind of processes. Okay. This oil cooler is similar to the jacket cooling that I just explained about generators, when you have to pour oil to lubricate and they get hot and all of that. Okay. So your furnaces, okay, your furnaces are also source of heat that you can recover. So common uses of this kind of heat, you can do preheating, you can do drying, you can do sanitary hot water where you need low-grade heat, you can do absorption chiller, you can do heat pump. We're going to talk about heat pump and some of these technologies as we continue. So checklist for heat recovery. Now, if you're going in an industry to conduct an audit, these are some of the things you need to check, right? Identify waste heat potential. Where are waste heat occurring in the industrial processes? Okay, so you can read up all of this one. I mean, it's self-explanatory. So there is what we call pinch analysis. Some of those who are chemical engineers, you'll be very familiar with pinch analysis. And it's a very simple phenomenon. What this simply means that for industrial processes, most of the industrial processes, if not all of them, is either you're adding heat or you're removing heat. Most of industrial processes, if not all, is either you're adding heat or you're removing heat. Now, exclusion of when you're talking about mechanical movement, where you need to convert the material from one point to the other. But for the process itself, it's either you're adding heat or you're removing heat, right? So pinch analysis is not saying, look, can you identify the places where you're adding heat and also identify the places where you're removing heat? Okay, so if you're removing heat from a certain substance, is it possible for you to transfer that heat that you're removing to a place where you need to add heat? So you don't generate a fresh heat, right? So what you're actually doing, you're moving heat from a place you don't want it, or a process where you don't want it, to a process where you want it. Okay, so that's what pinch analysis is trying to explain. So pinch analysis is a classical methodology for analyzing heat recovery potential for an industrial process or a total industrial site. Okay. A composite, then this is a report from a composite survey. To determine the heat recovery potential specific to the site, the individual temperature, enthalpy profile of cold streams are combined into one global profile, resulting in the so-called composite curve. And similarly, for the hot stream, resulting in the hot composite curve. Now, this is just what I explained. You have an industrial process where you need to remove heat. When you remove that heat, you don't need to throw that heat away into the environment because you have another process where you need to add heat. So you bring two of them. Now you can do this in your early design stage. You can bring two of them closer. So as you're removing heat from one process, you don't need to throw that heat away. You are now adding that heat to another process where you need to add heat. Okay, instead of generating a fresh heat. Now, let me give us an example of what is going on in Nigeria. In a hotel, if you go to a hotel, they have a generator, a diesel generator, and they are running on this diesel generator. 70% of the fuel content that goes into that diesel generator is converted as heat, and they dump that heat. That heat is dumped into the environment. But do you know that inside that hotel, they will now still convert that electricity, the 30% electricity that is generated from their diesel generator, they will now use it to generate hot water. So they are converting that electricity back to heat. Common sense will ask you, why not extract the heat from that generator and then use it and dump it inside your water and then use it to generate your hot water? It is something that is practicable. It's something that is doable. Instead of converting the electricity that has been generated back to heat. Okay, so is it possible to extract that heat from the generator and then use it to generate our hot water and then serve our guests in the hotel? So this is something similar to what pinch analysis is saying. Okay, instead of generating fresh heat with electricity, whereas you have a waste heat somewhere, collect that waste heat and use it for your desired purpose. Okay, so that's what pinch analysis is talking about. So let us talk about heat pump. Now, heat pump is similar to your air conditioning system, but opposite. Okay, your air conditioning systems absorbs heat from your space and it dumps it into the environment, right? But what your heat pump does is this: it collects the heat from your environment, it compresses it, and it becomes hot. It becomes hotter. Then you need to pass a fluid, maybe water, to collect that heat, and you're dumping that heat into your water. So you can use heat pump to generate hot water, from the air. We call it air to water heat pump. So it collects the normal air that you have in your environment, which maybe sometimes can be at maybe 30 degrees centigrade or 35 degrees centigrade. It compresses it and the air becomes hot, maybe 80 degrees, maybe 80 degrees centigrade or 90, okay, depending on the capacity of the compressor. Then you now pass that hot air through water. Water then absorbs it and the water becomes hot. That's what heat pump does, right? And that's what this diagram is trying to illustrate. So now this is your ambient air, waste or ambient heat. It comes into, it flows into this, okay. So here you have your compressor, right? So the ambient air passes through this pipe, right? Okay. So this is the ambient air that is coming in, and you have your compressor here, right? So your compressor, like I said, your compressor compresses this ambient air. It becomes extremely hot. Then it passes through this pipe. Then you now pass water, hot air for drying. This could be hot air, it could be water. But in this case now, they use air. So it's air to air, not air to water. The first example I cited, I told you was air to water. But in this case now, it's not passing air. So you pass another air to extract the heat from this low-grade ambient air. Okay. You now pass another air through the tube. Now, this is heat exchanger. Heat exchanger will keep reoccurring in most of the industrial processes. Anytime you see heat exchange, there is a heat exchanger. And in most cases, it's shell and tube heat exchanger. So in this case now, this is the shell. This rectangle you're seeing is the shell, and this is the tube. So the air that you want to heat is passing through the tube. And then the hot air or the hot gas is passing through the shell. Okay, so there is a exchange that is going on here, such that when this air is coming out, it's coming out hot. Okay, so the air actually comes in from here. Okay.
Sorry, I lost connection. Sorry, I lost connection.
Okay. Where did you start losing your connection?
The time where the hot air and the cold air in the condensate.
Okay, on this very slide, right?
No. The one with a green and this thing.
Here?
No? No, sir. Yes, yes.
Okay,
This is the
so
place I lost connection.
okay. So sorry about that. What's going to happen? That's like how many slides away because we don't have so much time. Don't worry, the video is being recorded, right?
Okay, sir.
The video will be shared to you, so you can always catch up with any session that you've lost out with. Okay.
Okay.
All right. Thank you so much. So let's proceed. Now, when you're talking about cooling systems, right, or heating systems, we're talking about heat pump. Either you're cooling or you're heating. How do we determine their efficiency status, right? Now, to help us determine the efficiency status, there's what we call performance measures. And performance measures, we mean coefficient of performance. Okay, now this is for heat pumps. We grade the efficiency level based on coefficient of performance. And what does coefficient of performance means? It simply means the useful heat. Remember that your heat pump, the essence of having your heat pump is to generate heat from your atmospheric air. It collects the atmospheric air and they use it to generate heat for you, right? So the useful heat that you get from that heat pump, all over the electric power that you put into that heat pump, the electric power that it draws to operate, okay, we give you what we know as coefficient of performance. That is COP for short, okay? So this is just a nomenclature, this is just a definition of what it is, okay? Useful heat energy added all over the energy consumed, right? So it can also be defined as the useful heat energy removed. In this case, if you're cooling, then it should be the heat that you remove, right? All over the energy that it consumed. But in this first case, it assumes that you're heating. So the heat that you added over the energy that it consumed, okay? So efficiency of refrigeration system and heat pump is denoted by its coefficient of performance. Now, this first one is for heating. This second one is for cooling. When you're removing heat, you're cooling. When you're adding heat, you're heating. Okay. So the efficiency of those systems is denoted by coefficient of performance, that is COP. It's very common when you're talking about heat pump for an industrial process, you'll be hearing something about COP. Even sometimes when you're talking about air conditioning system, you might hear something like COP. However, air conditioning systems are more suitable with EER. Is more predominant with EER. You see that, I'll show you that. So a high COP value represents a high efficiency, okay? COP is affected by the evaporator temperature and the condenser temperature. Higher the evaporator temperature and lower the condenser temperature, better is the COP. Now, let me explain this because it's very, very important, okay? I don't know if you understand what evaporator is and what condenser is. Now, let me explain that. Your air conditioning system, the unit that you have inside your house, that's an evaporator, okay? The unit that you have outside your house, that is the condenser. Now, the essence of the evaporator is to provide cooling. Now, the essence of the condenser is to expel heat, okay? The heat that your evaporator collects inside your house, when it gets to the condenser expels that heat to the environment. Okay, that is just a simple explanation. Okay, there are more technical explanations to this, but I just want you to understand what evaporator is and what condenser is. Okay, now the reason why it said that the higher the evaporator temperature, the better for you is that if you're running your air conditioning system and you put it at 17 degrees centigrade, you're going to consume a lot of energy, right? And that's why it's telling you that you need to increase that temperature from 17 to maybe 22. So the higher your evaporator temperature, the better your COP. Then it now went ahead to also tell you that the lower your condenser temperature, that's the one that's outside. Now you will notice that during cold weather, your air conditioning system seems to be more effective. Now, the reason is because the weather outside is cooler. Then the efficiency of the air conditioning system will improve. And that is what is playing out here. The lower the condenser temperature, the better your COP. Okay, so your air conditioning system, the best way to operate your air conditioning system is to, increase your evaporator temperature to a level that is comfortable, and then your condenser, try to see if you can provide shading so that it's not exposed to so much environmental temperature or weather temperature, right? If you do these two things, you're going to see a significant reduction in your energy consumption of your cooling system. Okay, so it's important that we understand this. So it's went ahead to tell you that 1% higher temperature of your refrigerant in the evaporator or 1 degree centigrade lower in the condenser improve your COP by 2 to 4%. So the temperature of your cooling system is very, very important. Whether the evaporator or the condenser is very, very important to their efficient status. So we need to pay attention to this, and we need to understand how they affect their efficiency, their performance. So performance measure continues. Now I talked about EER. EER means energy efficiency ratio. Now this is more applicable for air conditioning system that we use, in our homes and offices, right? You're going to see EER. EER means energy efficiency ratio. Now it is the ratio of cooling output in kilojoule. Kilojoule is energy, to the energy in watt hour to operate the system. So in simple formula format, EER is equal to kilojoule cooling output, because the essence of air conditioning is to provide cooling, right? So the cooling output divided by the energy it's consumed. The energy, not power. So EER, we can express it in both energy and power. So the first one is expressed as in the form of energy, while the second one is expressed in the form of power. Okay, so these are just formula that we should take note of. So now we can convert EER to COP. So assuming that you have a heat pump and you're giving the COP, but somebody is not asking you, look, I want this value in EER. I want to know what the COP is. I want to know what it is in EER. Okay, how do you do that conversion? That is where this conversion formula comes to play, right? Kilowatt electrical, that's electrical energy input divided by the kilowatt thermal, okay, is equals to 3.6 over EER, which is also equals to 1 over. Now, what I want you to take away, just note this formula. Most especially this 3.6 over EER is equal to 1 over COP. This part of the formula, okay? Just note them. Most of the formulas that we are throwing out here, I don't expect that you cram everything, but it's important that you know how to use them, so that when you see a question, you know the formula you're going to go and look for. Once you get the formula and you put them into, and that's the beauty about energy calculations. If you understand how to use these formulas, you will not have any problem in energy calculations. You will not have any problem. It's all about formula. Just get the right formula, put it, plug in the known values, and you get your answer straight. Okay. So let's just see an example. Okay. Find the EER of a heat pump having a COP of 4. Now you are given a heat pump. You know the COP to be 4. And now somebody is asking, I want to know what the value of this COP is in EER. Okay. So simple solution. Remember the formula I told you to take note of. 3.6 over EER is equal to 1 over COP. If you put down this formula, you put in what you know. You know what the COP is, which is 4. So the only thing you're looking for is the EER, and just cross multiply. By cross multiplying, you know what your EER is, which is 14.4. It's as straightforward as it is. Okay. So what if you're also giving the COP? No, if you're giving the EER and you are not asked to calculate the COP, it's the same thing you're going to do. Just apply the formula and you can do that conversion. So EER versus COP. Basically, the long and short is that EER is mostly for air conditioning, for cooling, while COP is for heating.
Hello,
So hello.
Yeah, please go back to the last slide. Yeah, the EER is 14.4. You didn't put any unit in the answer.
Yes, there is no unit. It is unitless.
No unit.
No unit,
But
please, sir.
the other slide before this one, you put, okay, unit in form of electrical, and in form of power and in form of energy.
Yes, yes. I'm trying to see. Yeah,
Okay.
there's no, so like I said, it is
It's a ratio. It's a ratio.
It's a
I've
ratio,
seen it.
yes,
Yeah,
yes,
yeah.
exactly. So
Thank you.
okay. So I was just trying to explain the difference between EER and COP. Mostly EER is used for cooling, air conditioning system, while COP is used for heating system. That's just the basic difference between two of them. But you can as well do the conversion, okay?
Yeah, yeah.
Please, you
Good
can
afternoon, how are you? I've
can
not
you
seen
please
my menu.
okay, I don't know. Do you want me to continue? Do you want us to take like 5 minutes, 5 to 10 minutes break? Or you want me to continue?
Continue.
I should continue. Okay. Okay, so let us look at building. Let me. Okay, let us look at the building heating, ventilation, and air conditioning system. Okay, so for short, this is known as HVAC. We call this HVAC. HVAC means heating, that is for H, ventilation and air conditioning system. So let us look at that, entirety in a building. So why is this so important? Why is HVAC so important? HVAC is significant energy user in building. Significant energy user, that is what SEU means, right? So significant portion of building energy consumption is for HVAC, and that's very important. That's why it's important that we understand energy efficiency in HVAC system. Now, for commercial buildings in US, it's about 51% of their energy consumption. In Spain, it's at 52%. In UK, it's 58%. Only God knows which country is this. Which country is KSA? Well, of course.
Saudi Arabia.
Okay, Saudi Arabia. Yes, okay. It's actually reflected because Saudi Arabia is the weather can be hot, right? So you can see that as much as 70%. In Bahrain is 71%. Okay, maybe we've not had a good research in Nigeria to present what the Nigerian value should be, and that is one of the problems that we have in Nigeria. We usually have difficulty, getting data about the Nigerian systems. Okay, so other issues, we talk about peak load, because air conditioning system is a significant energy user. We have to find a way to manage their peak, their consumption, especially when we have a limited supply. So if you're, for most of us that uses solar system, you find out that your air conditioning system is excluded from your solar system, right? Because it's a heavy energy user. Even when you're running your generator, most times you try to avoid, you size your generator not such that it doesn't have to carry your air conditioning system, right? Because it's a significant energy user. So it is very, very important, even when we are on public grid. It's also important that we learn how to manage the energy consumption of air conditioning system so that we can also curtail their peak load. Now, what we don't understand, maybe because in Nigeria we don't charge demand, there's no demand charge in our energy tariff structure, and that's why people are not conscious how they use their electricity. Okay, in US and other part of the world where they have demand charge, they charge you per demand. So it's more like you're contracting a certain size of your generator to power your house. So if you contract 20 kilowatts, you make sure you maintain your 20 kilowatt. If you go beyond 20 kilowatt, they will charge you. Okay. So for those kind of people, imagine that situation is prevalent in Nigeria. What it means that you're not going to run your AC, your washing machine, your dishwasher, you're not going to run them at the same time. You will find a way to space them so that you don't overshoot your peak. I don't know if that is making sense. So that is why it is important for us to understand how we can manage HVAC systems so that we can as well operate them within the limited capacity of supply option that we have. Okay. So, and it's also important for peak pricing, for cost issues. Of course, we know that air conditioning system is cost a lot. So we also need to understand how to manage them so that we don't spend so much on them. So now the question is, what induces cooling load? You come to an apartment, you come to your office, you're running air conditioning system, and these air conditioning systems they are costing a lot in terms of energy consumption. So what actually is causing this heating load? Because your air conditioning system is actually absorbing heat and throwing them out into the environment. So where are these heats coming in from, right? Now, heat flux through the building envelope. Okay, you have direct irradiation through your glasses, through your walls, and all of that. You have air leakages and ventilation, naturally or forced. Now, if you're running your air conditioning system and your doors are not closed or your windows are not tightly closed, then it's as good as you running an air conditioning system for the environment. Okay, because the more you try to pull out the heat from that space, the more heat from the environment is coming into that space, and it keeps adding to the workload of your air conditioning system, right? So human waste, we human will generate heat, and it is estimated that every human, we generate about 70 watts at 25 degrees centigrade. So human body generates it, and that heat needs to be evacuated. That's what AC does. It helps us to evacuate those heats so it can be comfortable. So there are also waste heat from your lighting, from your machines, from your televisions, from your fans, and all of those things. So all of these heat that have been generated in the space has to be evacuated, even including those that are now coming through the weather, through your windows, through your walls, and all of that. They need to be evacuated. And here lies the problem. For some of us that uses our air conditioning system and you turn it down to 17 degrees centigrade, or you turn it down to 16 degrees centigrade, this is what is actually happening. The more your air conditioning system tries to push out the heat in that your space, okay, the more it tries to drive down the space temperature down to 17, the more you create a gap between the weather temperature and your indoor temperature. And the more you widen that gap, right, the more you increase the pressure. The pressure from the atmospheric air in the outside will force themselves into your space. Okay, now it sounds technical, but if you don't understand it clearly, you don't need to worry. I was just trying to use it to explain why it is important we don't run our air conditioning system at the lowest temperature. Okay, so if you don't understand the technicalities, just understand that you don't need to run your air conditioning system at the lowest temperature. So at most, at worst case 22, at worst case 22, but at 24 you're okay. It also has another factor, which is humidity factor. Okay, humidity also plays a factor. Okay, and I think it has been captured here. Yes, very well, it's captured exactly. So now let us talk about thermal comfort. Okay, benchmark for thermal comfort zone. Now, indoor air temperature between 20 and 26 degrees centigrade, depending on activity, is fine. I told you 22, but here they're saying 20. Now, depending, there are some people that are very active. They have a very high metabolic activity. Okay, their body system has a very, very high metabolic activity rate, right? So for those kind of people, maybe 20, they might want to keep it at 20. But between 20 and 26, you're comfortable. That's not all. There's another factor, like I said, there's indoor humidity between 30 to 70, or maybe between 40 to 60. So as long as your indoor humidity is between this range and your temperature is between 20 to 26, normally most humans should be comfortable. So there's no point running your air conditioning system at 17 or 16 degrees centigrade. I keep emphasizing this point because it's a means through a lot of energy is being wasted by the air conditioning system. So another factor is airspeed. Airspeed below 0.2 meter per second at 20 degrees centigrade, if possible, 0.1. This is not necessarily significant, but again, it's something that is worth knowing. And there is another factor that is often neglected, but also important. Okay, is this carbon monoxide level, right? Now, this is applicable when you're in a conference hall, okay, where you have a lot of people. We breathe in oxygen and we breathe out carbon dioxide, right? So and when you're running an air conditioning system in that kind of situations, remember that your windows are closed, your doors are closed. If you're not careful, the level of carbon dioxide in that space might begin to increase, okay, and it becomes a problem. Okay. Now we advocate that when you're running your air conditioning system, close your windows, close your doors. But now I'm not saying again that look, it could lead to problem. right? So for this kind of situation, occasionally you need to just open up the windows, okay, so you can have you can have more like cross ventilation, like expel some of the CO2s and then bring in fresh air into the space. And we also need to understand that how our air conditioning system work. Some of us are of the opinion that our air conditioning system takes air from outside, clean it, make it cold, and throw it inside our space. No. Air conditioning system, it takes the air inside our space, clean it, make it cold, and throw it back into the space. So it's not taken from outside, except for some certain configurations, okay, where you now have economizer. Okay, so some air conditioning system use that, but it's not very common. So when you now switch into an economizer mode, what that means is that it's just taking air from outside, especially when the weather outside is cold. That's when you use economizer mode. If the weather outside is cold, you now put it into economizer. So what that means is that it's going to take cold air outside and throw it inside your house. But it's a rare case. I mean, this is rare. Okay, so it's very important that we understand all of this, how air conditioning systems work and what keeps the human body comfortable. So what can be done? A well-designed building can reduce the heating and cooling load by up to 30%. Now, this outcome can be raised by adding passive design features or construction measures. Now, so for example, if you paint your light color for the building envelope, if you paint your building white, outside space of your building, if you paint it white, okay, what does it can reflect back some of the sun radiation that are coming into that building. So it's not transfer, the rates of heat absorption into the wall, which now eventually gets into your house, can be reduced. That's one. Two, shading. You can apply external shading to break the sun from hitting your walls. Okay. So by so doing, you'll reduce the amount of heat that is coming into your house. You can also do air tightness of your windows, your doors, and all of that. Double glazed windows is not very common in Nigeria, but in other world, Western world, is very, very common because of their very cold weather, right? So double glazed windows is also another way. What this means that your windows are tightly closed, and then you have a glass such that more like you have two parallel glass, and then you have a space in between the glass. So that space you have in between the glass, there's a gas that is filled in between those spaces. They're high in heat resistance, right? That's what double glazed window means. It's not common in Nigeria. Okay. Then, of course, your roof insulation. I don't know why some people would decide to put black roof on their houses. It's very common in Nigeria. And we all know that black absorbs heat. Okay. Yes, black absorbs heat. Okay. So I don't know if it's just for the beauty, because of sometimes it can look beautiful, maybe because of the aesthetics, it looks beautiful. But technically speaking, energy efficiency wise, it is not recommended. It is not good. Okay. So then you now talk about your wall insulation. How do you insulate your wall so that you prevent heat from coming into that building? Okay. So the bottom line is that a well-designed building can reduce heating and cooling load by up to 30% from the design stage. Right? You can begin to implement some of these measures. So this is Lagos, Nigeria. If you look at this building, you can see how they have kind of insulated the walls with green vegetations, right? And then this is another one. If you look closely in this image, you will see how they they had some kind of awnings. I mean, kind of extension from the walls to prevent sun radiation from hitting the walls, for hitting the glass directly. So this is another one. Back then in my school, I know I've seen this kind of structure. This middle picture is very, very common in my school. I remember very well. My university in Futo, we have this kind of we have structures with this kind of aesthetics, right? And the whole essence is to prevent solar radiation from gaining access into the building, right? So now, but this is not Nigeria, this is Austria, okay? So now let us talk about electric motors. Electric motors is very, very important because it consumes a lot of energy for most industrial processes. So motor drive a lot of things, okay? Whether in the industry, in our home, even in our phones. A lot of us don't know that our phones has motors. You know that vibration that you feel when your phone vibrates? It's motor that does that work. Okay, so motor is almost everywhere. You know, your fans, motor drives your TVs, your laptops. You know, the fans inside your laptop, your TV, and all is driven by motor, right? So application is huge. So we need to talk about it extensively. So 70% of commercial energy consumption is converted by electric motor. That is an obvious fact. So motor efficiency play a big role. The motor efficiency has improved a lot from smaller motors. Motor efficiency can be kept high by proper maintenance. But most problems are within the design of motor-driven application and system. Now, this is very important. When we talk about motor system, there might not be so much you can do on the motor itself, okay? But somebody asking again. Engineer Odafe, you okay? No, I'm trying to read a message that Engineer Odafe left.
So he said motor is the most used, followed by pump, which is
yeah, exactly.
Industry.
So now what I'm saying is this, right? When you look at motor applications, in most cases you might not be able to do so much on the motor itself, but you forget that motor is a driven application, that is drives processes. So the processes that motor drives, you can achieve a lot of energy savings from those processes, not from the motor itself, but from the processes that motor drive. Okay, that's what this is saying. That's what this caveat is saying, that most problems are within the design of motor-driven applications and system, not by the motor itself. So electric motor life cycle cost. Now, the life cycle cost of the electric motors is maybe assuming that the motor is operating for like 3,000 hours per year and it operates for about 7 years, right? Now, putting this assumption into perspective, you're going to see that the energy consumption cost of that motor is 95% for that 7 years. So the capital cost that you use in buying that motor is almost insignificant, 3%. So it's very, very important that when you're buying motor, you need to buy a motor that has a higher efficiency rating. Because the one with lower efficiency rating might cost lower, but that is insignificant. The bulk of the expenses is in running that motor, in operating that motor, right? So you can see from these statistics that 95% total cost of owning that motor is in the electricity consumption, right? So what are the potential savings? Okay. Now, like I said earlier, 60% saving can be achieved from mechanical system optimization. Mechanical system optimization means the motor-driven applications, not the motor itself, right? If you optimize your mechanical system, then you can then rightly size your motor so that it does not consume, you don't oversize your motor, right? So sometimes you're operating motor and you're operating them at a very low load factor. Okay, so which means you oversize the motor, it becomes a problem, right? So now 30% can be done using electronic speed control. Now this is where VSD, variable frequency drive, comes into play, right? If your motor is oversized, you can, instead of changing it entirely, you can actually deploy VSD to tune it down so that it can match the load that it is carrying, right? So that's where VSD comes into play. So the next one is increased use of energy saving motors. Okay, so you need to buy more energy saving motors. There are different classes of them. I thought, okay, I know it's somewhere. It's somewhere in the slide, but it would have been more appropriate if I presented them here. There are different classes of energy motor classifications in terms of their efficiency level. But let's proceed. Now let's talk about what motor does in generally. So the whole essence of you having motor is to convert electrical energy into mechanical energy, period. That's what motor does for you. It converts electrical energy into mechanical energy. So therefore, it is very important that we understand the equation that connects these two. Kilowatts electrical, kilowatts mechanical. We need to understand that. So here you can see that this is three-phase. This three-phase power, it could be either kilowatt or kVA. This is an apparent power, okay, coming into this motor. Then, of course, the motor now transforms this electrical energy into mechanical energy and it comes out in horsepower. Then you're using the rotational speed to power your load. Okay, that is the whole essence of having a motor. And we know power factor. Power factor is equal to kW over kVA, period. We know that. Now we know the input power, the input energy to this motor. The input energy is kilowatt electrical. That's input. And it is given by this equation. Cube root 3 times kilovolts times kilovolts or voltage, but in this case I've added K, so it's now kilovolt, okay, times power, times amperage, times power factor, right? If I take away this power factor, it becomes kVA, but because we have power factor, so it is now kilowatt. Now this is kilowatt electrical. We are going to see how to convert this kilowatt electrical to kilowatt mechanical. But let us understand that kilowatt electrical, this is the formula for kilowatt electrical. So this is what is coming into the motor. Input energy. Okay. So like I said before, if you remove this here, it becomes kVA. So I also illustrated that here. Now let us look at the formula that helps us connect kilowatt electrical to kilowatt mechanical. Now this is the formula. It's written in red. Kilowatt electrical is equal to kilowatt mechanical. Now, kilowatt mechanical is output, the shaft output. When you look at the name, when you look at the nameplate ratings of motors, you're going to see their capacity. What you're seeing there is kilowatt mechanical. When you look at the nameplate, this is important. The capacity written on the nameplate of your motor, of the motors, is the output energy. The power output of the shaft, which is kilowatt mechanical. Okay, so in most cases, you will now be asked to calculate the energy input, which is kilowatt electrical. So because you can know what the kilowatt mechanical is if you look at the nameplate, but you now have to calculate what the energy consumption will be. So you can do them in two ways. You can actually measure it. You put a clinometer, you measure it, or you can now do your normal calculation, right? So now this is the formula that correlates kilowatt electrical to kilowatt mechanical. Kilowatt electrical is equal to kilowatt mechanical times load factor divided by efficiency. Now, when you look at the nameplate of your motor, you always be given this efficiency rating. They will tell you the efficiency. They will tell you the kilowatt mechanical at certain efficiency, right? There's no motor that is 100% efficient. Okay, so they might say, okay, certain kilowatt mechanical at 90% efficiency, right? So the load factor depends on the load that you're giving to it. Okay, so you need to know what load is given to that motor. The higher the load, the higher the efficiency. Okay, so kilowatt electrical and kilowatt, I've explained it. These are inputs to the motor. Why kilowatt mechanical is the motor nameplate rating or output? I've explained this already. So now let us try and make kilowatt mechanical subject of the formula. This is just normal formula manipulation, okay? Normal subject of the formula making and stuff like that. So if we try to make kilowatt mechanical subject of the formula, what we have is that kilowatt mechanical times percentage load, this load factor, percentage load is equal to kilowatt electrical times efficiency. So more like cross multiplication, right? So this is what you have. So for a single phase line, if you're dealing with a single phase motor, right? So this is the formula you're going to use. Kilowatts, this kilowatt is kilowatt mechanical times the percentage loading. They have to take the percentage loading. If you're not given the percentage loading, just assume it's 100% load. Just assume it's 1. If you're not given, just assume 1, right? But if you're given the percentage loading, so if you're told that this motor is loaded at 50% of its capacity or 30%, then you have to, put them here. Then you have your kilowatt electrical. When you open up this, your KWE, kilowatt electrical, when you open it up, you have voltage times current times power factor. And then, of course, times your efficiency. So this component is your kilowatt electrical. Then for three-phase, it's the same thing, only that in this case, you're not introducing the cube root. right? The cubic root is the same thing as 1.73. If you punch cubic root on your calculator, you're going to get 1.73. So it's the same thing, only that you're introducing 1.73 because it's a three-phase. So let us take note of these formulas, please. So let us do a simple sample problem here. So during my last energy audit, I saw a 75 kilowatts mechanical electrical motor that had the following information on the nameplate. Now it's 400 volts, 131 ampere, that is the current, and it's a three-phase motor. Now I'm told that it is 92.7% efficient, or at full load, meaning the percent load factor is 1. So what is the power factor of the motor, of this motor? So we are not, this case, you are not even asked to calculate the kilowatt electrical. You are being asked to calculate the power factor of this motor. Okay, we are given sufficient data to do that. So let us try and do that. So in most cases, you have to first of all determine the kilowatt electrical. Indirectly, they are not asking us to calculate the kilowatt electrical, but there's no way you'll be able to get your power factor if you don't know what your kilowatt electrical is. Are you with me? So now let us first of all calculate what the kilowatt electrical is. So the first step for us is to find the kilowatt load the motor is drawing at full at the full load condition. So we use the motor mechanical equation. So now this kilowatt electrical, right, is equal to kilowatt mechanical times load factor all over efficiency, right? Now we know what the kilowatt mechanical is. Okay, we know what the load factor is, and we know what the efficiency is. So it's just simple. We just put in the values. Our kilowatt mechanical is 75, right? Our load factor is 100 at 100, so it's 1. Our efficiency is 92.7, so 0.927. So once you put that into this formula, we get 80.9 kilowatts electrical. Okay. So now, secondly, what we're going to do, now we know what the kilowatt electrical is. We know that the formula for kilowatt electrical is equal to the cubic root times kilovolts times current times power factor. Now we don't know power factor. That's what we are told to find. We know what the current is. We know what the kilovolt is. We know what the kilowatt electrical is. Okay, so we now put this 80.9 for kilowatt electrical. We know what the kilovolt is, 0.4, which is the same as 400 volts. We know what the current is, which is 131. Then we don't know what the power factor is. So from here now, we can then calculate what the power factor is. And that's what we did here. So when we put in the values here, we'll calculate for what the power factor. So from our calculation, the power factor here is 89.1%. That's what the power factor is. I hope we understand this sample problem. Okay. So let us look at another problem. A three-phase induction motor is drawing 12 amperes at 440 volts. So we know what the current is, we know what the amperage, the voltage is. If the operating power factor is 0.8 or 80%, then the power drawn by the motor is dash. So now they're asking us for kilowatt electrical. What is the power drawn by this motor, right? Let me just show us the solution. It's simple and straightforward. Okay, so now the kilowatt electrical, like I said, first of all, we know it's a three-phase motor. And we should keep in mind that if it's a three-phase motor, we must introduce this cubic root here. We must introduce this cubic root, then times our voltage times our current times power factor. Now, this is a straightforward question. So once you plug in the known values, okay, you know what your kilowatt electrical is, and it's 7.3 kilowatts. Let us look at another example. A three-phase induction motor is drawing 10 amperes at 400 volts. If the operating power factor of the motor...
Hello?
Okay.
Hello? Yeah, you go to the other slide. You were saying cube root. I think it's square root of 3, not cube root.
Square root of 3, yes.
Yes.
Yeah.
So that will not mix.
Sorry. Yeah,
No, no.
sorry. Yeah. Thank you very much for that.
You are
So
welcome. Welcome.
yeah. So
Go
just
on,
a
go on.
moment. Yeah, I understand. So just so that we don't get this mixed up, right?
Yes, yes.
Yeah. So it is not square root of 3. Sorry, it is cube roots, not square root of 3.
Cube root.
Yes, cube roots.
Sorry, if it is cube root, the
Yes.
figure has to be inside the square root of the thing.
Sorry?
Are you getting
Outside the
it
square.
Is root 3. Let us say
now? It's
root 3.
root
Let's
3.
say
It's root 3. Uh-huh.
Okay. No.
It's root 3, not
Root 3.
cube root.
Okay.
Yeah, root 3.
Okay. So root 3, right?
3.
Exactly,
Yeah.
exactly.
Okay. So sorry about that. So it's good that you brought it up so that we are very clear. Sometimes
Yes. You
the
don't do
nomenclature.
now.
Yeah.
You don't say now when you don't do all these things. You are just speaking in small.
Yeah.
Since you have
So
done it before now.
yeah, exactly. So this is root 3, right? Okay.
Yes.
Thank you. Thank you for that. Yeah. So let's proceed.
Yeah.
Okay. So a 3-phase induction motor is drawing 10 amperes at 400 volts. If the operating power factor of the motor is 0.85 and the motor efficiency is 90%, then the mechanical shaft power output of the motor is dash. So in this case now we are
Kilowatt.
in this case we are looking for the kilowatts. Can you attempt this question? We are looking for the kilowatt mechanical in this case. I don't know if it's something you can attempt. Let me just give like one. This is a simple one, but let me give you like one or 2 minutes for you to try this. It's very important so that I understand that you're also following the training. If you have the answer, just you can speak up. You can unmute yourself and speak up. Has anyone arrived at an answer? Once you get the answer, just unmute yourself and say, or you can type it in the chat box. Please, I need someone to give us an answer.
I think the answer is 5.3 kilowatts.
Sorry,
5.3 kilowatts.
5.3 kilowatts. Okay. Does anyone has a different answer? Okay, let me just show that. So 5.3 kilowatt is the answer. Yes, very correct. Very correct. Omolade, thank you so much. Did anybody got something different from 5.3? So maybe we can kind of try to understand why you're getting something different. Okay, so I assume that someone left a message in the chat. 5.2, yeah, it's 5.3 kilowatt from engineer Dafe. Yes, correct. So let's proceed. So it's good that we understand this relation between kilowatt electrical and kilowatt mechanical. So here's another sample question. I don't want this answer to show. It's not coming out clearly the way I want it. So a 22 kilowatt rated three-phase induction motor operating at 405 volts and drawing 18 kilowatts, 32 amperes will be operating at what power factor? Will be operating at a power factor of what? So in this case, we are now asked to calculate the power factor. We are told it's a 22 kilowatt rated three-phase induction motor. Here, this 22 kilowatt is what? Is it kilowatt mechanical or kilowatt electrical? Can somebody say?
Kilowatt electrical.
Kilowatt electrical. No, it's kilowatt mechanical. A 22 kilowatt rated three-phase induction motor is operating at 405 volts and drawing 18 kilowatts. Now, this 18 kilowatt is the kilowatt electrical, right? So, and that is now 32 amperes. And it's not asking us what power factor will it be operating at, okay? So it's important that we understand the difference between kilowatt electrical and kilowatt mechanical. I've told you that the ratings on the electrical motors are the output, their shaft power output, which is kilowatt mechanical. So here is what the solution is, right? It's something that we know. The kilowatt mechanical is equal to the kilowatt electrical times. In this case, we are not giving the load factor, are we? So if you're not giving the load factor, I've told you that if you're not giving the load factor, we assume it to be at full load, which is 1. I stated here, load factor is not given, so assume full load, which is 1 in this case. So it's the same formula that we have, the root 3 times the voltage times amperes times the power factor divided by the load factor. Okay, so we are now, first of all, I think we need to, okay, we are looking for power factor. So we can look for power, we can actually calculate power factor direct from this formula, right? We know every other thing, but we don't know what the power factor is. So it's simple, it's a straightforward question. Okay, so here we can calculate what the power factor is, all right? So now I think there's a little bit of confusion here. Because the total is drawing 18. Can anyone hear me? Hello?
Yes, we are hearing
Okay.
you.
Okay.
Yes, we can hear you.
Okay, because it looks like maybe I lost connection. I wasn't so sure. Okay. So the drawing, this 18 kilowatts, that's kilowatt electrical that is being drawn here. I think it's just to see if maybe we actually fall to the part of using the 18 kilowatts, okay? Because we'll be giving the voltage, we'll be giving the amperes of what is drawing, okay? So we need to, on our own, be able to calculate what the kilowatt electrical would be, okay? And not just using this 18 kilowatt. I think this 18 kilowatt is just a trap to see if we are just going to take this 18 kilowatt and then substitute here to do our calculation, right? So this is just, the essence of this question is to help us differentiate when we are to find kilowatt mechanical, when we are to find kilowatt electrical. And that was why I asked, this 22 kilowatt, what does it represent? So the 22 kilowatt is kilowatt mechanical. So the solution is quite straightforward and simple. You don't need to do any, you don't need to calculate kilowatt electrical before you find out what your power factor is in this case. So here's a test question. I want us to answer this. I don't think it requires even calculation. It requires our critical thinking. An induction motor rated for 75 kilowatts and 90% efficiency, operating at full load, will do that. If you know the answer, unmute your mic and speak. The rated, now this is kilowatt mechanical. The 75% is kilowatt mechanical. And we have been told that it is operating at 90% efficiency. At full load, right? Will it deliver 83.3 kilowatts? Will it deliver 75 kilowatts? Will it draw 75 kilowatts, or will it draw 67.5 kilowatts? $75 kilowatts and 95 kilowatts and 90% efficiency, it's operating at full load. Anybody answer to this?
67.5.
Sorry? 67.
G.
So it's going to draw 67.5. Does somebody have a different answer? Someone has a different answer. So let me not waste so much time on this. So the answer is actually going to be that it is going to deliver 75 kilowatts. That is B. Now the thing is this. This 75 kilowatt is the rated output of this motor. And this 75 kilowatt rated output is when the motor is operating at 90% efficiency, right? And they told us that this motor is now operating at full load, right? So everything is optimum. So since everything is optimum, it is actually going to give out the rated output, which is 75 kilowatts mechanical. Does that make sense? I need to hear someone. Hello? If you don't understand it, if you feel it's confusing, please speak up. Can anyone hear? It's confusing. Now,
yes.
when you pick up an electric motor and you look at the nameplates, they're going to tell you some certain things. They're going to tell you the capacity of that motor in terms of kilowatts. Now, the kilowatt they're going to tell you is the kilowatt mechanical output of that motor. Okay? And they're also going to tell you the efficiency of that motor. Right? So if they tell you that efficiency of that motor is 90%, that efficiency of 90% is at full load. So they will not tell you that when that motor is operating at full load, at 90% efficiency, that motor is going to give out 75 kilowatt mechanical shaft power. This information is going to be there in your nameplate. So when these conditions are met, right? When these conditions are met, it's operating at a full load. at 90% efficiency, which is the ratings that has been inscribed on the nameplate, then the output will actually be 75 kilowatts. Is that okay now? Or is this still confusing? Okay.
It's okay now.
Okay. So here is another test question. A facility has a motor that draws 200 kVA and has a power factor of, sorry, Engineer Uche,
Yes.
do you have this presentation?
I think I've sent everything.
No. So what I want to do, I want to shut down. I want to switch supply.
Okay.
Right. So what I wanted to do, if you have, so you can project so that they can be doing this exercise while I do that.
Okay. Let me.
Yeah, I have few exercises. I also have the solution, but I want them to try it on their own before I present them with the solution.
Okay.
Right?
Let me. Yeah. I think I'll open it now. It's okay.
Okay. Okay.
Yeah.
So that wouldn't take me up to 5 minutes. I'll just come back.
Okay. Have we gone past here? Okay, we are here. Please, let's continue the debate. Somebody was saying about not getting it. Hello, any contrary view? Let's make it interactive. Okay, let's go to the next question.
Hello.
Yeah.
Okay, I wanted to say something on the other question
Okay.
regarding the data given. We were given some 5 kilowatts.
Mechanical.
Yeah, mechanical. And
At
that
90%.
efficiency is 90%. If something is working at 90%, it's working at 2 something. And the load factor is 1. Which means the thing will deliver the same 75%. Like the other example you mentioned for us when you were introducing this stuff. You made an example of something that we'll be able to compare it and see that it can carry the same load with what we are saying. Are you getting my point, sir?
I'm getting you, but what's your final verdict, sir?
The final verdict is 75 kilowatts.
Okay, so you agree with him?
I agree with it in totality.
Okay, do you have a contrary view?
No.
Not you, I mean another person, any other person in the class with a contrary view? Okay, let's move to the next one. Let's move to the next one. Let's also attempt this one. A facility has a motor that draws 200 kVA and has a power factor of 0.707. What is this one is straightforward now. How many kilowatt does it draw? Power factor is watts over kVR.
We were not given current. Hello?